Screen sharing screen sharing screen sharing. Everything alright.
Good morning, dear students.
Morning, sir.
Very good morning.
Good morning.
Good morning. Good morning. We are going to start our physics session. As of now, I am going to mute your voice and I'm going to take you class. Please listen to this class carefully. The contents which we are going to discuss are very important in the field of physics. So you better follow each and every content what we are discussing now. Okay, let us start with this one, torque and angular acceleration. Let us start with the torque and angular acceleration. Torque and angular acceleration. Actually, you might have come across these ideas that objects can undergo linear and rotational motion or translational and circular motion. Those bodies which are undergoing linear motion must be dealt with certain physical quantities like force, displacement, acceleration, momentum, force, etc. If the same bodies are undergoing circular motion, then they cannot be dealt with the same physical quantities. They must be dealt with the quantities like the force gets transformed to torque, force in rotational form gets the name torque, mass becomes moment of inertia. Moment of inertia, I can write moment of inertia. Moment of inertia. Then displacement goes as angular displacement. Then acceleration becomes angular acceleration, and so on. We can just keep on writing the names here. Actually, the left side, the physical quantities which I have mentioned on the left side, deals with the objects which are undergoing linear motion, and the physical quantities which we are having on the right hand are said to be dealing with the objects which are undergoing circular or rotatory motions. Now we are discussing about the rotational motion of bodies. So these ideas are all very important. The torque, moment of inertia, angular displacement, angular acceleration, etc. Here we are going to speak about the relation connecting torque and angular acceleration. We are going to discuss about the relation connecting torque and angular acceleration. We are considering the rigid bodies which are undergoing circular motions. So we shall speak about that. Let us consider a rigid body which is undergoing rotational motion about a fixed axis. So let me mark this as a fixed axis, and let it be the rigid body. Actually, this one is the rigid body. Rigid body is a solid body. It's a rigid body. Actually, this body is said to be a rigid body, which is undergoing a circular motion. This is a rigid body which is undergoing a circular motion. Being a solid body, I'm just giving a shade over here. This is a fixed axis. And this one is the rigid body. Fine. Let me take this as the and just mark the boundary of this one here. Let's consider this rigid body. Fine. This is the fixed axis about which the rigid body is undergoing a rotational motion. Is undergoing a rotational motion. Actually, if you consider a coordinate axis for your understanding, I can simply explain it here: x, y, z. Actually, this rigid body is undergoing a rotation in the x is the plane, and the y axis is the axis of rotation, fixed axis of rotation. Actually, this is the fixed axis of rotation. Let me rub it off and then very clearly once again. So this is the xy z axis. Actually, in this x z plane, the object is undergoing a circular motion about the axis y. So this is the vertical axis, fixed axis. Now I am considering a point mass. I am considering a point mass m in this rigid body, because a rigid body is supposed to be made up of large number of point masses. So I am assuming, I am considering a small mass m, which is at a position vector, let me say r. Actually, this is at a position vector r. And it is acted upon by a force F. It is acted upon by a force F. And this force is acting along this particular direction. It is acted upon by the force F. And it is undergoing a circular motion. Actually, this is undergoing a circular motion. This mass m is undergoing a circular motion. Why am I showing you a ellipse to explain about the circular motion is that this is moving in the plane. This point mass m is moving in the plane, x, z plane. So in a two-dimensional diagram, it appears to be an ellipse. Actually speaking, it is undergoing a circular motion. So about the axis, about the fixed axis, the rigid body is undergoing a rotational motion. The rigid body is undergoing a rotational motion. And this rigid body is supposed to be made up of large number of point masses. I am considering a point mass m over here, which is acted upon by a force F. And the mass m is at a distance r. We used to call this as a position vector because it defines the position of the mass m from the axis of rotation. Fine. If this force F acts on the mass m, what will happen? This force acting on the mass m produces a torque on the point mass. So a torque has been produced due to the force acting on the point mass. So we can say here the torque produced by the force on the point mass about the axis can be expressed in the new formula here. So the force F is perpendicular to the position vector of the point mass, and this force acting on the point mass produces a torque, so that it is undergo a rotation. It will undergo a rotation. Torque is nothing but a rotational force. So it will be undergoing a rotational motion. The mass M will be undergoing a rotational motion. So the torque acting on the point mass about the fixed axis can be written with this expression. Actually, you have come across the expression for torque already. So I am going directly. Torque is equal to, actually the vector form of torque is tau vector equals r vector cross f vector. I am writing its magnitude. So tau is equal to r f sin theta Actually, I have mentioned earlier, this F vector and R vector are acting at right angles to each other. So the angle between the position vector and the force vector is 90 degree. So I can write RF sine 90 since theta equals 90 degree. Sine 90 is 1. Simply I have RF and we can write this as RMA since F is equal to MA. Force equals mass into acceleration as per Newton's second law. And also you can write this as mr square alpha. Tau equals mr square alpha since A equals R alpha, which is the relation connecting linear acceleration and angular acceleration. So A equals R alpha is the relation connecting linear acceleration and angular acceleration. Actually, what is the base with which we are approaching this idea is that the entire rigid body is supposed to be made up of large number of point masses. So the first thing what I am doing here is I am calculating the torque experienced by a single point mass. And then if I sum up the torques produced by or produced on each and every point mass, then I will get the total torque acting on all the n number of point masses, which is nothing but the rigid body. Or a rigid body 10 point mass நால ஆனதுன்னா ஒரு பாயிண்ட் மாஸ் மேல எவ்வளவு டார்க் அப்ப 10 பாயிண்ட் மாஸ் மேல ஆக்ட் ஆகுற டார்க் எல்லாத்தையும் கால்குலேட் பண்ணி சம் பண்ணோம்னா டோட்டல் டார்க் கிடைக்கும். And that total torque is the torque experienced by the rigid body which is undergoing a rotational motion due to the action of force F. That is the idea. So I am going on with the calculation for torque acting on a point mass. Then I will switch over to the torque acting on a rigid body and I will bring out the relation between torque and angular acceleration. This is the key idea. So I am writing here the magnitude of torque is tau equals RF sin theta, which is RF into sin 90, which is RMA, and A, F is equal to MA. Actually, I have changed F as MA and A is equal to R alpha. So the expression goes as tau equals mr square alpha. In vector form, I can write tau vector is equal to mr square into alpha vector. mr square into alpha vector. What is this term mr square? This is the moment of inertia of the point mass. Moment of inertia of the point mass. This is the moment of inertia of the point mass. So mr square denotes the moment of inertia of the point mass. What is moment of inertia? It is nothing but the rotational inertia. Moment of inertia is nothing but the inertia of rotating bodies. This is expressed as moment of inertia. So moment is turning effect actually. Moment here refers to turning effect. Turning effect. So if any object is said to be undergoing circular motion, it will also experience an inertia. We call it moment of inertia. So moment of inertia of the point mass is expressed as mr square. So tau vector equals mr square alpha vector is the expression for the torque acting on a point mass. Torque acting on a point mass. Fine. You can say here that the torque and alpha are acting along the axis of rotation. They are all acting along the axis of rotation. In this diagram, I can show you here. In this diagram, I can show you here. I am writing the expression in the vector form as tau equals r vector cross f vector. Tau vector equals r vector cross f vector. If you apply right-handed rotation rule, r vector towards f vector, you just extend this r vector along this direction. It's not clear. I can change the color over here. R vector is along this direction. you rotate R vector towards F vector. So R cross F, thumb will be projected upwards. So this is the direction in which the torque acts. As we have obtained the relation tau vector is equal to mr square into alpha vector. Tau vector and alpha vector are said to be acting along the same direction. So I can write tau vector and alpha vector acts along the axis of rotation of the rigid body. Tau vector, the torque, alpha vector, the angular moment, angular acceleration, both are acting along the axis of rotation of the rigid body. So if I am considering the point mass, the position vector acts along this direction and the force is acting along this direction and the R vector is rotating towards F vector. So the resultant tau vector will be acting perpendicular to the plane containing R vector and F vector. As we would have come across this statement in vector analysis, we can say here tau vector acts perpendicular to the plane containing R vector and F vector. R vector and F vector. So tau vector acts perpendicular to the plane containing R vector and F vector. So tau vector will be acting along the axis. If tau vector is acting along the axis, alpha vector will be also acting along the same direction. And we can say here, if tau vector and alpha vector are along the same direction, are acting along the same direction, then the point mass will undergo, or the body will undergo angular acceleration. If it is acting in the opposite direction, if tau vector and alpha vector are acting opposite to each other, or in the opposite direction, or acting in opposite direction, then the body will undergo, this is an important idea which you should know, body will undergo angular deceleration. Which means if tau vector and the alpha vector are acting along the same direction, the rotation takes place further and further. It keeps on accelerating, so it will keep on rotating. If tau vector and alpha vector are acting in opposite directions, then the body will undergo angular deceleration. So the rotation gets slowed down. The rotation of the rigid body will get slowed down when tau vector and alpha vector are acting in the opposite directions. Moreover, I can say here this tau vector, alpha vector, omega vector, all these vectors are axial vectors. They are all axial vectors. I can say here tau vector, alpha vector, omega vector are all axial vectors. Specifically, this omega vector, this tau vector won't move the object anywhere. So the object will not move along the direction of tau vector or direction of omega vector or direction of alpha vector. Actually, this tau vector and omega vector are axial vectors. You cannot expect the object to be moving in the upward direction. That won't happen actually, right? So if I say angular velocity, then that doesn't mean that the object will be moving along the direction of omega vector. That won't happen. So we can say here these are all axial vectors. They act along the axis of rotation, and nothing moves along this particular direction. But thing is that because of the existence of this vectors, axial vectors, the rotation of the body takes place. Rotation of the body takes place. As we saw here, tau vector equals mr square alpha vector. Here, mr square is the moment of inertia of the point mass, and this tau vector is the torque torque acting on the point mass. But as I told you, a rigid body is supposed to be made up of so many number of point masses. Rigid body is supposed to be made up of so many number of point masses. This kind of point masses sum up, point masses get summed up and then forms a rigid body. This is the key idea. So if a single point mass experiences a torque here, there are n number of point masses, then the moment of inertia of all the point masses is, or you can say here, the moment of inertia of the rigid body is the sum of moment of inertia of all the point masses. So a rigid body is made up of many such point masses. Hence, the moment of inertia of the rigid body is the sum of, if I want to calculate the moment of inertia, mi of a rigid body, the moment of inertia of a rigid body is the sum of moment of inertia of all the point masses. All the point masses. So, you can easily calculate the moment of inertia of the rigid body here. I can write it as the total moment of inertia. This I is the moment of inertia of rigid body. Actually, I is the notation for the moment of inertia. Right? So, moment of inertia of the rigid body is equal to sum over I equals 1 to n mi ri square. Mi ri square. So, I equals sum over I equals 1 to n mi ri square. This is the moment of inertia of the rigid body. What I have done is, I have summed up the moment of inertia of all the point masses from 1 to n. So I am getting the total moment of inertia of the rigid body. Now the torque acting on the rigid body, or torque acting on the rigid body. Earlier we wrote the torque acting on a point mass. Now we are writing the torque acting on a rigid body. This is equal to sum over I equals 1 to n mi ri square into alpha vector. Tau vector is equal to sum over I equals 1 to n mi ri square into alpha vector. Actually, this is the summation of the moment of inertia of all the point masses. So I can write here tau, the torque acting on the rigid body, tau vector is equal to I into alpha vector. Tau vector equals I into alpha vector. So tau vector is equal to I into alpha vector, where I is the moment of inertia, alpha is the angular acceleration, tau vector is the torque. Actually, this is equivalent to that of F is equal to ma in case of linear motion. F is equal to ma in case of linear motion. F is the force in linear motion, whereas tau is the torque in angular motion. M is mass in the linear form. I is moment of inertia of rotational bodies in angular form. A is the linear acceleration, alpha is the angular acceleration. Thus, we arrived at the result of the torque acting on the rigid bodies, that tau vector is equal to I into alpha vector. So, simply what we did so far is that we have first calculated the torque acting on a point mass, which is a constituent of a rigid body. After calculating the torque acting on a point mass, we have calculated the torque acting on a rigid body, which is tau equals, or tau vector equals I into alpha vector. The moment of inertia, the idea of moment of inertia will be learned, and its significance for bodies of differentials will be learned in section 5.4. It's given in the text, because we are going to learn about moment of inertia in the detail in the forthcoming contents. Now we shall speak about angular momentum. So this is the relation connecting tau vector equals I into alpha vector is the relation connecting torque and angular acceleration. And once again, I am telling you, if the torque and angular acceleration are acting along the same direction, then the rigid body will get accelerated. If tau vector and alpha vector are acting in the opposite direction, then the rigid body will undergo deceleration. Deceleration is nothing but retardation. Retardation is otherwise negative acceleration. Negative acceleration in the sense we can say the object will be slowing down when the torque and angular acceleration are acting in the opposite direction. When they act in the opposite direction, right? Moment of inertia is the inertia of a body in rotational motion. Inertia of a body in rotational motion. So, if you want to calculate the moment of inertia of a rigid body, it is the sum of moment of inertia of the individual point masses. So, I equals sum over I equals 1 to n mi ri square. So, torque tau vector for a rigid body is given by the expression tau vector equals I into alpha vector. Tau vector equals I into alpha vector. Now, can just go for angular momentum. This is the next idea which we have to discuss. We shall speak about angular momentum. Momentum is the study of quantity of motion possessed by a body. Momentum is a term. It's the quantity of motion possessed by a body. If body of mass m moves with the velocity v, then it is said to be expressed by a term p vector equals mv vector, linear momentum, product of mass to velocity. இவ்வளவு மாஸ் இருக்கக்கூடிய பாடி இவ்வளவு வெலாசிட்டியோட மூவ் ஆகுது அப்படின்னு சொன்னா அதுக்கு எவ்வளவு மொமெண்டம் இருக்கும். அதுதான் மொமெண்டம்ங்கிற குவாண்டிட்டி. அப்போ மாஸ் தனியா வெலாசிட்டி தனியா பேச வேண்டியது இல்லை. They are clubbed together and they are dealt with a single term, momentum. So momentum in Tamil undam அப்படின்னு சொல்றோம். undam. So momentum, this is in linear form. When you are speaking about the same momentum in angular form, we call it angular momentum. So the momentum possessed by the rotating bodies or the bodies undergoing circular motion is termed angular momentum, right? So angular momentum in rotational motion is equivalent to the linear momentum in translational motion. So angular momentum in rotational motion is equivalent to the linear momentum in translational motion. Translational in the sense linear. Any object which moves along a straight line path is mentioned as translational motion. So angular momentum is for rotational motion. Linear momentum is for translational motion. And further, angular momentum is or angular momentum of a point mass is defined as the moment of linear momentum. Moment of its linear momentum. Whose linear momentum? The point mass is linear momentum. Angular momentum of a point mass is defined as the moment of its linear momentum. You can say here, you can consider a rigid body. Same diagram. I'm not going to give out the shade now. The same rigid body which is rotating about an axis, fixed axis, and this is a point mass. It is acted upon by a force F. Everything is okay, but the thing is that actually we used this action of force to calculate the relation between torque and angular acceleration. Here I can say actually this point mass is at a distance, let us say r, position vector is r, this is the point mass having mass m. It's, let me say, because of the action of force, it moves with the velocity v along this direction. This product of mass into velocity will give you momentum p equals mv. Actually, if this rigid body undergoes a rotational motion, then we can say if this rigid body undergoes a rotational motion, yeah, fine. If the rigid body undergoes a rotational motion, then we can say then we can say this is the moment of its linear momentum. Actually, this point mass is experiencing a moment. As I told you, moment is nothing but turning effect. Moment is nothing but turning effect, as I told you earlier. So moment of linear momentum is turning effect of linear momentum. If this linear momentum produces a rotational motion in the rigid body, then we call it the moment of linear momentum. We call it in short as angular momentum. So angular momentum is moment of linear momentum, right? So angular momentum of a point mass is defined as the moment of its linear momentum. The moment of its linear momentum. In other words, the angular momentum L of a point mass, the angular momentum is generally expressed in terms of L. L vector is the notation for angular momentum. So the angular momentum L of the point mass having a linear momentum P, which is at a distance, let us say R, can be expressed in its vector form as L vector is equal to R vector cross P vector. L vector is equal to R vector cross P vector. L equals R cross P. So linear momentum of a point mass having a linear momentum P, which is at a position vector R, can be expressed as, actually this is P vector. So where in what direction the angular momentum will act along the axis, L vector will act along the axis. Once again, you have to go for this rotational right-handed rotation rule in vectors. R vector rotating towards this momentum vector P vector. So R vector towards P vector will produce a L vector or the third vector in the upward direction. So if R vector undergoes a rotation towards P vector, then L vector will be acting in the upward direction. So L vector equals R vector cross P vector. So this is giving you the moment of linear momentum. A point mass at a position or at a distance R is experiencing a momentum P, and it is undergoing a rotation which produces an angular momentum L. So L vector equals R vector cross P vector. In magnitude, I can write L equals RP sine of theta. L equals RP sine theta, where theta is the angle between R vector and P vector. This is theta. Theta is the angle between R vector and P vector. Actually, theta is the angle between R vector and P vector. And L vector is perpendicular to, as I told you, L vector is perpendicular to the plane containing R vector and P vector. This diagram seems to be clumsy. I can show you here once again with the coordinate axis. You can understand this. Actually, this is the path in which the rigid body is undergoing a rotational motion. Let me say this is the point mass. This is experiencing a momentum. Sorry, P equals mv. P equals mv, and this is the position vector R. Here, R vector and P vector are existing in the xy plane. R vector and P vector are existing in the xy plane, and L vector will be acting in the z direction. So the angular momentum vector acts in a direction which is perpendicular to the plane containing R vector and P vector. Angular momentum vector acts in a direction perpendicular to the plane containing R vector and P vector. As we have written in the case of torque, we can also write the torque, or we can also write the angular momentum by adding sin theta either with R vector or with P vector. Actually, I have written the magnitude here, L equals RP sin theta. This magnitude can be expressed by adding sin theta with either R or with P. So I can write this as R into P sin theta, where this is RP perpendicular, or otherwise I can write L is equal to R sin theta into P. This R sin theta can be written as R perpendicular into P. R perpendicular into P. So what does this indicate? We can simply say momentum vector is perpendicular to R. This is the perpendicular component of momentum vector. Actually, P perpendicular is perpendicular component of momentum vector. Momentum vector. So we can say here, if we take the product of R, position vector, and the perpendicular component of momentum vector, we will be getting angular momentum, magnitude of angular momentum. In the same way, this is the perpendicular component of position vector. R perpendicular is the perpendicular component of position vector with respect to momentum vector. So we can say here, if you take a product of position component of position vector, perpendicular component of position vector with the linear momentum, we will be getting the magnitude of angular momentum. So angular momentum where content is simple. Either take a product of position vector with perpendicular component of linear momentum vector, or take a product of perpendicular component of position vector with linear momentum vector. Both of these products will give you the magnitude of angular momentum. Both the products will give you the magnitude of angular momentum. As I told you, the vector form of angular momentum is L vector equals R vector cross P vector. L equals R cross P. And I can say L vector acts perpendicular to the plane containing R vector and P vector. Fine. We can say here the value angular momentum L equals 0 if P equals 0. Linear momentum is 0, or the position vector R is equal to 0. If linear momentum is 0, which means if the rigid body is not experiencing any linear momentum, if the velocity acting on the point mass is 0, linear momentum is 0. If linear, actually P equals mv, right? This is the momentum of a point mass. If the point mass is not moving, velocity is 0. If velocity is 0, linear momentum is 0. If linear momentum is 0, L will be 0. Simple. And in the second case, we can say the angular momentum is 0 if the particle is at the origin. R equals 0. If this particle P is at the origin, actually this is O. If this point mass is at this position, at the origin, then R will become 0. The position vector will become 0. Then also we can say L will be 0. If R is 0, L will be 0. If the point mass is at the origin, if this R equals 0 indicates the point mass at origin. If the point mass is at the origin, then L is equal to 0. Here also the angular momentum is 0. Also, L will be equal to 0 if R and P or R vector and P vector are parallel or anti-parallel to each other. Parallel or anti-parallel to one another. That means theta equals either 0 or 180 degree. Theta equals either 0 or 180 degree. Nothing is there. From the simple expression L equals RP sin theta, if R is 0, L is 0. If P, linear momentum is 0, L is 0. If theta is 0 or 180, then L is 0. That's it. So the angular momentum value will be 0 if the linear momentum of the point mass undergoing rotational motion is 0. If the point mass is existing exactly at the origin, then also the angular momentum value is 0. And then if the linear momentum and the position vector are acting parallel or anti-parallel to each other, then also we can say the angular momentum value is 0, which means theta is now becoming 0 or 180 degree. Fine. This is all about the angular momentum. This is all about angular momentum. Generally, there is a misconception that the angular momentum, the physical quantity angular momentum, is associated only with the objects undergoing rotational motion. It's not true, actually. The angular momentum is also associated with the bodies which undergo linear motion. We can understand this from the following example problem. So, one thing you should keep in mind that the angular momentum is associated with both. I can highlight it here. Angular momentum is associated with both linear as well as angular motions. So I can write angular momentum is, actually this is an important question which you should know. Angular momentum is associated with both rotational motion and the linear motion. Rotational and linear motion. Angular momentum is associated with both rotational and linear motion. I can just give you a simple example just for your understanding. For your understanding, I can tell you. This is a four-way. A circle is there. A circle is there. A four-way. Actually, circle in the sense, I'm just telling you, a four-way is there. A bus is coming along this direction, Another bus is coming along this direction. Actually, these drivers haven't noticed the vehicles. Actually, this fellow, first one, this fellow is second fellow. Actually, the second fellow has came exactly in the middle of the road, and this fellow is coming faster. If he happens to hit this bus at the stick, what will happen? What will you observe? What happens to the bus 2? Just imagine what happens to the bus 2. Bus 1 is hitting perpendicular to bus 2. What will happen to the bus 2? It will begin to rotate, right? It will begin to rotate. Actually, it will undergo a turn. It will rotate actually about some axis. It will begin to rotate about some axis because of the action of this force, right? Actually, this is moving with certain amount of momentum and hitting the second bus. So the second bus is experiencing a circular motion. If the second bus is experiencing a circular motion, then we can say it is undergoing an angular momentum. It is experiencing an angular momentum. If second bus is experiencing an angular momentum, what provided this angular momentum to the second bus? That angular momentum has been provided by the first bus. A bus which is moving in a straight line path, or is it possible for a bus moving in a straight line path to provide angular momentum to another bus to undergo a rotational motion? Do you understand my question? A bus moving in a straight line path is providing angular momentum to the second bus. How come this is possible? Thing is quite simple. If someone is asking me money, then I can provide them only when I have money, right? If I have money, I can provide them money. If I have energy, then I can spend the energy. If I have angular momentum, I can provide angular momentum. So, a body moving along a straight line path or a linearly moving body should have or would have possessed an angular momentum so that it has been transferred to the second bus at the time of impact. Thus, we can say a linearly moving object will also experience this angular momentum. Don't confuse yourself. Angular momentum is not only associated with the objects undergoing circular motion. Angular momentum is also associated with the objects undergoing linear motion. So this example would have given you a simple idea about the understanding of angular momentum associated with the linear motion. You can apply this to any of the other live examples. Actually, some doorway is there, a glass doorway which is pivoted at the middle is there. Actually, you are moving, you are walking along the straight line. And if you are pushing the doorway, what happens? The door is undergoing a rotational motion, right? The door is undergoing a rotational motion if it is pivoted. Which means it is experiencing an angular momentum. So a linearly moving body, which is you, are providing the angular momentum to the rotating body, which is nothing but the doorway. So there comes the simple example or simple understanding that the angular momentum is associated with both rotational and linear motions. Actually, an example is given related to this content, what we are talking about. A particle of mass m is moving with a constant linear velocity v. Show that its angular momentum about any point remains constant throughout the motion. Its angular momentum about any point, you are going to assume some point, remains constant throughout the motion. Okay, we can see this example. Example number 5.11. Let me say a mass m is undergoing a linear motion. It is possessing a velocity, constant velocity v. So it has a momentum p equals mv, right? As this velocity is constant, this linear momentum is constant. Mass won't change. As this value is constant, it moves along a straight line path. It moves in a straight line. It moves in a straight line. Now assume some point O as an origin. About this point, we are going to calculate the angular momentum, and we are going to say the angular momentum is constant, right? So you are assuming a point O, which is at a distance d from the path along which the point mass is moving. At some instant, actually this is the position vector, let me say r vector. At some instant, this position vector OQ or this position vector meets the point mass at the point Q. At the point Q. Actually, this point mass is moving along this path. As it reaches this point Q, this position vector is meeting this point Q at some instant. And we can say here, this is the direction in which this r vector is acting. P vector is acting along this direction. This is angle theta. This angle is also theta. For requirement, I am writing this is also angle theta. Fine. This is also angle theta. Fine. R vector and P vector are acting along this particular direction. By taking this product between R vector and P vector, I can calculate the angular momentum L vector. And theta is the angle between R vector and P vector. I can write angular momentum as L vector equals R vector cross P vector. I can write RP sin theta. Here R is nothing but OQ. R is nothing but OQ. So in your text, it would have been given as OQ P sin theta. And we can write it as R into mv sin theta, since P equals mv. And we can write it as mv into R sin theta or OQ sin theta. mv into R sin theta or OQ sin theta. Actually, this is L, right? My magnitude L. L equals mv into R sin theta or OQ sin theta. And what is this OQ sin theta? What is this OQ sin theta? See this one, we can see here. Actually, this is R, right? If I resolve this into components, this is R cos theta component, and this one is R sin theta component. So this R sin theta is nothing but D. So we can write here R sin theta is nothing but the D, which is the distance between the point or the assumed point and the path along which the point mass is moving. So angular momentum can be written as L equals mv into D. Angular momentum equals mv into D. So it is the product of linear momentum multiplied by distance. Product of linear momentum multiplied by distance. So angular momentum is equal to P into D. Here we can get the clear picture that actually it is moving with a linear momentum. But about certain point, we can calculate at any instant. It is also this point mass possesses angular momentum also. So a linearly moving body possesses an angular momentum, which is given by the expression L equals mv into D. L equals mv into D. And we can say here that as V is constant, this P is constant. Actually, momentum, linear momentum P is constant. And the distance D is constant. Actually, D is the perpendicular distance from the point. If I assume a point here, then the distance will be the same. If I am assuming the point here, the distance will be the same. This distance, perpendicular distance, won't change. Don't confuse yourself. Actually, this distance from the point from the origin to the path along which the point mass is moving is a constant. As you assume the same point over here, and this is the path of the point mass, then the distance will be the same. So D is constant, P is constant, then L should be constant. So linear momentum is constant. The distance between the path of the point mass possessing linear momentum and the axis about which the angular momentum has been determined is a constant. So angular momentum is a constant. If suppose the point mass moves along this path, if the point mass moves along the origin, then what will happen? L will be equal to 0. This is also constant. As long as the value of or as long as the point mass moves along the origin, the angular momentum remains a constant. L equals 0. So we can say here, as long as the linear momentum is maintained a constant, the distance D is maintained a constant, the angular momentum is always a constant. So we have proved the required idea in the given question. Fine. And we can say here, when will you increase the angular momentum? Or how can we increase the angular momentum? Either you have to increase the mass. So if the mass of the point is of greater magnitude, then the L can be increased. If velocity V is increased, L can be increased. If V is increased, L can be increased. But we have given the data that V is a constant, so L is a constant. And then if D is increased, suppose if the point mass is moving from here, if the point mass M is moving with the velocity from here, then the distance increases, so the angular momentum will also increase. So angular momentum increases with the increase in the value of point mass, increase in the value of velocity, and increase in the value of distance D between the point about which the angular momentum has been determined and the path along which the point mass is moving. So MVD increases, angular momentum increases. As long as this MVD are maintained constants, the angular momentum remains a constant. So this is all about the idea of torque, the relation between torque and angular acceleration, and about angular momentum. And the final idea is that angular momentum is not only associated with the rotational bodies or bodies which are undergoing rotational motion. It is also associated with bodies undergoing linear motion. Thus, we can say the relation connecting torque and angular acceleration is tau vector equals I into alpha vector. And what is angular momentum? Is the moment of linear momentum of the point mass. Moment of linear momentum of the point mass. How will you express this angular momentum? L vector equals R vector cross P vector. The cross product of R vector and P vector gives you angular momentum. What is magnitude of angular momentum? Rp sin theta. Rp sin theta. And we can say the angular momentum can be determined either by taking a product of the perpendicular component of position vector with the linear momentum, or by taking a product of the perpendicular component of linear momentum with position vector. Linear momentum with position vector. Fine. And finally, we have concluded that the angular momentum is associated with both angular rotational motion as well as linear motion. And we saw an example also. I would like to conclude at this point. We shall discuss in the next class. Thank you.